Taylor polynomials. So yesterday, so we finished doing force and stuff, but we didn't actually talk about Taylor polynomials at all, right? Okay, I wasn't sure. Okay, so let me just real quick kind of talk about the idea. So we're going to spend quite a bit of time talking about this now, and then even later in the next chapter, we'll also spend, well, in chapter 10, we'll spend quite a bit of time talking about Taylor polynomials in a different sense. But here's the idea. The idea is that you have a function. It could be whatever, any function. And, it could be a simple function, but it could also be a very, very, very complicated function, as long as it's reasonably well behaved. And so you remember that, so let's say we've got a point here, let's call this A. And you remember in Calc 1, you talked about approximating functions using what? You guys remember? Approximated functions. You found the derivative, and then you found, what did you do a lot of? Had a function, you found the derivative, then you found the, starts with a T, second word's an L. Starts with an L. TL. Tangent line, yeah. Remember, you found tangent line. It's all over the place, right? You find the derivative, and then you find the equation of the tangent line. And so the tangent line, if I find the tangent line at this point, looks like roughly like that. If I was able to draw a straight line, that's what it would look like. So, and do you guys remember the equation of this? So this was called the linearization of f of x at a. So you called it maybe L of x, and that is equal to the value of the function, f of a, plus the slope at the point, which is equal to the derivative, right? So f prime at a times x minus a, right? So, okay, so this is the point slope form of a line, and so you did this a lot in last semester or whatever you took first semester calculus, right? Okay. So this is a polynomial. Do you guys agree? Polynomial of degree what? What's the degree of this polynomial? One, right? 1, right? Because the x has a power of 1, and so that's the highest power you have. Okay, so the question is, okay, so, and the other key thing to notice is that, so note that the value of the y value of the line is equal to the y value of the function. Do you guys agree with that? Okay. Do you also agree that the derivative of the line, the first derivative, is equal to the first derivative of the function? Yes? Because the derivative of the function is equal to the slope of that line because they came from the same place, right? That's the equation of the tangent line, so the derivatives have to equal each other, right? Okay, so, all right, so this right here, so we're gonna call this something different. So this is called the, so we're gonna rename. This is gonna be T1 of x. So this is the first degree, or degree 1, Taylor polynomial of f of x centered at a. Okay, so this is just a name that we'll expand on this in a little bit, but But the key thing is this, is that the value of the function and the first derivative are equal to. So then you ask yourself, okay, so that's nice, but notice that we're talking about approximating the red function with the line. Once you go away from that point, what happens? Like if I wanted to approximate the function over here with this line, would that be a good idea? Absolutely not, right? Because it would be how far off? Way off, right? A lot. It would be off by a lot because you would be approximating. So the value of the line is way down here. The function is way up here. So not a good plan, right? So the idea is, okay, so these two, they have the same y value and the same first derivative. So can you come up with a function so that the second derivative is also equal to? And then we can extend that, and what if the third derivative was equal? And then what if the fourth derivative was equal? And what if the fifth? And so on and so forth. Yes? That's the plan. So the idea is that, and we'll do this in real life and we'll show you, is that, so what does a second degree polynomial look like? A parabola, right? And a third degree can have, so if you have a polynomial, right, and it has a certain degree, you can have how many humps?
1 minus?
Yeah, 1 less than the degree, right? So a parabola is degree 2, so it has 1 hump. Degree 3 can have 2 humps. Degree 4 can have 3 humps. Degree 5 can have 4 humps, and so on and so forth. So the idea is that if you keep increasing the degree, so this is, I'm just totally making this up, but the idea is that if you have a second degree polynomial, maybe let's say it looks like something like that or something. So that approximates it for a little bit longer, right? And a third degree could maybe look something like, again, totally making this up, but let's just say something like that, right? And so if I increase the degree, the idea is that hopefully it follows it for larger intervals. Yes? Okay, so we're going to talk about how do we create these polynomials. So, oh shoot. Oh well. Okay, so let's set this up. So I'll actually go up here. Okay, so we'll start with, so we already know T1. So let's do, let's say we want to find T2 of x. So this would be called the what? Second degree. Yeah, Taylor polynomial. T2 of x for f of x centered at a. So what are the requirements? The requirements are that the value of the function should match the first derivative and the second derivative, right? So we're going 1 degree higher to see if we can do a little bit better than what we had before. So the requirements are that the value of the function, the polynomial, so T2 of a should equal to f of a. The first derivative at a should equal to f prime of a. And then the second derivative at a should equal to f double prime at a, right? So this is what I want. So I want function, first derivative, and second derivative to match. Okay. So so T2 of x should look like, so it's going to be a second degree polynomial, right? So I'm going to write it in this specific form. So I'm going to just say it's going to equal to some number a, which I don't know where it is, plus some other number b times x minus a, bless you, and then plus some other number c that I again don't know where it is, times x minus a squared. And if you compare that to what we had earlier, it looks very similar, at least the beginning part of it, right? So do you guys agree that the first two terms, if I took out that last term, doesn't that look a lot like the first degree polynomial? Yes? Oh, yeah. Go ahead.
Just to clarify, T2 of A is the tangent line or the tangent function at point A, or how are they related again?
Well, T2 is the second degree Taylor polynomial, which we don't know what it is yet.
Okay, what is it in relationship to the function?
It's, so T is also a function. It's a polynomial. So, but when you say T2 of A, you're saying the y value of T at A. Just like when you say f of A, that's the y value of f at A. If you say T2 prime of A, that's the derivative of T at A. Does that make sense? So let me go back to the picture again. So right here, this is, so my function is the red function, right? So f of A is the y value. F prime at A is the derivative, or the slope of the tangent line. And here in this case, T, well, I didn't write it down explicitly that way, but T1 at A is equal to f of A, right? So what I'm saying here is that the y value of the two are the same. And when I write this down, T1 prime at A is equal to f prime at A, I'm saying that the derivatives of the two are equal to.
So they're always going to have those points in common.
Mm-hmm. Yeah.
But it's not necessarily the tangent, or is it?
For this, yes. For the first degree, it has to be. Because if you go to a point, a point on a function, that point has a particular derivative at that point, right? Mm-hmm. So how many lines are tangent to that point? Yeah, there's only one tangent line, right?
But
so, go ahead.
But if it intersects the function more than once.
Right, then it wouldn't be a tangent line, right?
Oh, so it's not necessarily the tangent.
It is for one point, whatever it's centered at. So this particular point, so like for example, if I find the tangent line right here, well, it would be the tangent line for that point only, right? So it can hit, it wouldn't be the tangent line for all the points. That's why it's always centered at one point. Always. Does that make sense? Kind of, sort of. Yeah, there's some confusion there. But I think maybe, let's keep going. But yeah, stop me if there's anything that is not clear. So what we're trying to find is the equation of the, in this case, parabola that has, so at a point, so that the y value, the derivative, and the second derivative are equal to each other. Yes? So this means that, so the y value, the first derivative, which is the slope of the line, and then the second derivative, which represents the concavity, right? So the concavity would equal at that point. So it would be, follow it closer. Yes? That's the idea anyways. Okay. So these values A, B, and C, we don't know what they are, so we want to find them. So, okay, so we want to find, let's do A first. So let's do, based on, let's number these. Let's say this is requirement number 1. So using requirement number 1, T2 of A, what is T2 of A equal to from plugging it in up here? If I plug in A into this polynomial, what do I get? Just capital A, right? Because what happens to this term? 0 in this term? 0. Okay. So T2 of A is equal to A. So that means that A has to equal to F of A, right? F of little a. Does that make sense? So based on requirement 1, then that value, that capital letter A, has to equal to F of A. Do you guys agree? Okay, now, for requirement 2, I need the derivative to equal at that point as well. So let's first find the derivative. So T2 prime of x, what is that equal to? B plus 2c times x minus a to the 1, right? So I just found the derivative of T2. So the derivative is equal to this, right? And I want that. So this means that t2 prime at a, which is equal to what? If I plug in a into that expression, what would I get? B, right? So what do I want that to equal to? I want that to equal to f prime at a. So then that means that b has to equal to f prime at a, right? So notice that I found a and I found b. And what do you notice about both of those, a and b? They are constants, but let's say I get rid of that c, x minus a squared, what would it look like? Yeah, it's exactly like the other one that I had, right? Isn't that so? If I get rid of that second degree term, notice that it looks exactly like that right there, right? Does that make sense? So it's going to be exactly the same. It doesn't change just because I increase the degree of the polynomial by 1. So that's good because that means that it's consistent, and if I increase the degree, it's always going to be, the beginning is always going to be the same. Yeah?
For the second requirement, is t2 prime, is it prime of x or prime of a?
Well, this is, the last one is t2 prime at a because it's at the point. But to find that, I had to get the derivative first.
So why didn't you do that for the first one?
Why didn't I what?
Why isn't it t2 x for the first requirement? The one right above it.
At the top?
No, like the one right above number 2. Why is it t2 instead of t2?
Oh, because, well, the only reason why is because I already know what t2 of x was, but I hadn't found t2 prime yet. So I have to find it first before. So it's the same thing with the third requirement. I don't know what the second derivative of t is, so I have to find it first, right? Just like I did right now for t2 prime. So the second derivative at x is equal to what? 2c, right? So, so this means that, so t2 double prime at a is also equal to 2c, right? Because it's just a constant. But, so what is that? So I'm trying to find c, right? So I want this to equal to the second derivative, right? So I want 2c to equal to the second derivative at a. So this means that c has to equal to 1/2 of the second derivative, right? Does that make sense? You guys with me?
I think that makes more sense if we were using numbers because it's pretty.
Well, we have to do it in general, otherwise then we just have, formula for one case. Well, we'll do an example after. Not to worry. But so if I'm going to write it down, let's write it down. So I have t2 of x is equal to, I have this first one, f of a, right? So f of a plus b, which is f prime at a times x minus a, and then plus c, which is this one, right? 1/2 f double prime at a times x minus a squared. Okay, and what is this called? This is the second degree, or degree 2 Taylor polynomial centered at a. So, but the idea is, notice how the first two, so if I remove the very last term from it, it's basically the first degree, right? So if I find the third degree, how many terms would it have? 4, right? Well, what do you know about the first 3? they would be exactly the same as these, right? So if I want to find the third degree Taylor polynomial, the first three would be exactly the same, and then I would add another term that would have a x minus a to the third power times some other number, right? So, okay, so the question is, well, how long is it going to take us to see the pattern? Because there's a pattern emerging. So like if I ask you, let's say I want to find t, the third degree. Can you tell me, so I know that the beginning is going to be exactly the same, right? Would you guys be able to tell me the next term, what it looks like? It's probably going to have a, what kind of derivative? Third derivative, right? And an x minus a to the third, right? But can you tell me the number that that's going to be in front? It's not quite there yet, right? Can't really see it yet. Okay, so you will be able to see. So we know, so far, all right, so this is what it looks like, right? So t3 of x is going to equal to, so if, I mean, we're not going to do the whole thing all over again because the same thing would happen, but we know that it's going to look like this, right? F of a plus f prime of a times x minus a plus 1/2 second derivative of a times x minus a squared. Okay, so this is going to make the function first and second derivative equal. But then I want one more term that has some constant d that I don't know what it is, times x minus a to the third. And I want this to be so that the third derivative at a, I want that to equal to the third derivative of the function at a. Does that make sense? So the same exact thing that we've been doing, just now extending it one more. So the question is, well, what is that that d there? So let's use so let's find the third derivative of t3. So notice what happens, when I get the first derivative, what happens to the first term? It goes away, right? 0, because that's a constant. When I get the second derivative, what happens to the second term? It goes away, right? Because it's a constant. If I get the third, first, second, if I get the third derivative, what happens to the third term? It's going to go away. So the only thing left is going to be, if I get the third derivative, the only thing left is going to be the very last term, and you're going to get the derivative of that one 3 times, right? Does that make sense? So what is it, when I get the third derivative, so the first, second, and third terms are going to go away, because every time you always lower the degree by 1, right? So those will go away, and what will the last term look like? When I get the first derivative, it looks like, you bring down the 3, right? So 3, and then dx minus a squared, right? You get the second derivative. You're going to bring down the 2, d times x minus a to the 1. Then you get the third derivative. You bring down the 1, which I'll just write it down just for emphasis, right? And then times d. Does that make sense? So you bring, every time you get the derivative, that exponent comes down, and you lower the degree 1. Come down, lower the degree 1. So then that means that, so this is, I'll leave it like this, 3 times 2 times 1 times d. What do you want that to equal to again? You want that to equal to the third derivative, right? Isn't that what we want? So we want the third derivative of t3 to equal to the third derivative of the function, yes? So what does d equal to? 1/6. And actually, I'm going to write it down like this, though. Because you guys can kind of see what's going to happen here, right? Kind of, sort of. So let's go back here. So this is going to look like, so let's switch this up. So this right here, I'm going to plop it down right there. So this is going to be 1 over 3 times 2 times the third derivative at a. Okay. Now, can you see the pattern? Like, could you see what's the next term going to look like? If I add, so if I do T4,
1.1.
so if I do T to the 4 of x is equal to all that stuff, right? Same stuff. Let's do 1 over 3 times 2. I'll just rewrite this one. So the beginning is going to be exactly the same, right? But what's the next term going to be? Yeah, 1 over 24. Where does the 24 come from? Yeah, 4. It would be 4 times 3 times 2. And then the fifth would be 5 times 4 times 3 times 2. And 6 times 4. So this would be 1 over 4 times 3 times 2 times, we'll just put the 1 for emphasis, f to the 4 at a times x minus a to the 4th, right? And that's how it would continue, right? So now that we see the pattern, now we can write it down. So let's write it down in general. So let's do, so we have t n of x is equal to, so let's write down a couple. F of a plus f prime at a times x minus a plus, let's do f double prime at a times x minus a squared over 2 plus dot 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 plus the nth derivative at a times x minus a to the n over. Now, how do you write, how do you express multiplying a number and all of the numbers smaller than it? What is it? Factorial, right? The exclamation mark. So this is called n factorial. How many of you guys have seen the factorial before? Okay, that's good. So n factorial just means you multiply, so like 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 100 factorial is 100 times 99 times 98 times 9, and so on. Yes? Okay, all right. So just making sure. So if I write this in sum notation, this would be the sum, k equals to 0 to n, of the kth derivative at a over k factorial times x minus a to the k. So that's exactly the same formula. So this right here, all right, so this is called the nth degree Taylor polynomial of f of x centered at x equals to a. Okay. So let's do an example. And so before we do an example, do you guys have any questions so far? Yeah.
Could you ever have a Taylor polynomial that's a degree higher than the function itself?
Well, yes, because the function can be anything. So it does. The function itself can be, for example, it could be, a trig function, and those, it doesn't really have a degree. Different kind of function.
What if it's linear?
Well, then the Taylor polynomial would just be itself. Right? If the function already is a polynomial, then the Taylor polynomial is basically itself. Because you would get exactly the same thing. Yeah.
So like what's like a general reason to use this?
Well, you can use it like if you have a very complicated function. So a function that is, imagine a function that has things all over the place, right? So all over, just sines, cosines, tangents, whatever. And so what you can do is you can turn that function that's very, very complicated. You could say, okay, well, I'm only interested in how this function behaves in this interval. So I will create a polynomial, which is a simple function that goes through those, and then that is very easy to deal with. So that's the idea. So that's sort of what it looks like, but then there's all sorts of other things that come from this. That you can derive a whole bunch of things, and we'll see some of them later on for sure. So let's say we want to find, let's do t, how about t5 of x, and we'll just do a simple function. We'll do sine of x centered at x equals to 0. Okay. So so what do we need? Well, we need the function and the derivatives, right? And then what is a in this case? In this example? 0. So a is equal to 0. So I have my function, and I'm going to need up to what derivative? Fifth derivative, right? So let's do that. So we'll find all 5 derivatives. So we have f of x is sine x. The first derivative is equal to what? Cosine x. Second derivative is equal to negative sine x. Third derivative is, what is it? Negative cosine. Okay. The fourth derivative, fourth derivative is sine again. And the fifth derivative is cosine of x. Okay. So, but we're not interested in the derivatives themselves, only at the point that we're evaluating. So in this case, it's at 0. So what is f of 0? So we just plug in 0 into all of those, right? So sine of 0 is just 0. And then f prime at 0, which is cosine of 0, or 1. Second derivative at 0 is negative sine of 0, which is again 0, right? The third derivative at 0 is equal to negative 1, right? Fourth derivative is, again, 0, and then the fifth derivative is positive 1. So those represent the part of the coefficients of every term, right? Each one of the terms. So if I use my formula, then what this is going to look like is, so I have, okay, so you guys have this in your brain or on your paper? Is there somewhere? Because I'm going to write it down here. Okay. Oh my gosh. I can't do that. Okay. All right, over here. So T5 of x. So the fifth degree Taylor polynomial is equal to, what's the first term? 0, right? So it's f of 0, which is 0, okay, plus f prime of 0, which is 1 times x minus a, but what is a? A is 0, right? So it's just going to be x. Okay, and then the next term is plus the second derivative at 0, which is 0 times x squared over 2. So I'm just writing, I know this is going to be 0, but I'm writing it down anyways, just so that you guys can see. So plus, what's the next one going to be? The third derivative, right? So that's going to be minus, let's do minus 1 over 3 factorial, which is 6x to the third, right? You guys agree? You guys with me? Okay, and then the next one is going to be 0x to the fourth over 4 factorial, right? And then the next one is going to be plus 1x to the fifth over 5 factorial. And so then, of course, you can keep going, right? Can you guys see what the next term is going to be? X to the 6 over 6 factorial, and then x to the 7th over 7 factorial. And okay, so let's get rid of all the zeros. So this is 0, this is 0, this is 0. So then I have t5 of x is equal to x minus 1/6 x cubed plus x to the fifth over 5 factorial. Or what is 5 factorial? How many? 120, yeah. Okay, so what is T6 going to be? I go to degree 1 more. How many x to the 6s would I have? 0, right? So actually T6 is the same as T5 because there's no, you would get a 0 times x to the 6. What would T7 look like? X to the 7th, right? Over 7 factorial, right? Would it be positive or negative? Negative. And then after that, if you keep going, what would the next one be?
8 to the 0, 9 to the
X, so positive x to the 9th over 9 factorial. So for fun, let's do this. So fun, well, fun plus you're going to have to do it later. But so before I show you nice pictures, let's see if we can write down Tn. So for any, well, let me actually, I'll get rid of this for now. So I want to write down the general formula for this one. So here, this is going to be fun actually. Okay, so, I don't know if you guys agree, but oh well. All right, so I'll write down the first part again. So x minus x cubed over, I'll write it down like this, 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. So plus dot, 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 plus. So in general, it's going to look like this, right? So I have some fraction, x to some power, but so, okay, what do you notice about all the powers? They're odd, right? So how do I write down, if I want to go through giving n values, so n equals 0, n equals 1, n equals 2, and 3, but I want them to turn into only odd numbers. How do you write that? Yeah, 2k plus 1. So in this case, we're using n. So in general, the power would look like 2n plus 1. Right? So notice that when n is equal to 0, then that exponent is 1. If n is equal to 1, the exponent is 2 plus 1, which is 3. When n is equal to 2, the exponent is 2 times 2 plus 1, which is 5. So it's always going to be odd, right? And then what do you notice about the exponent and the denominator, the numbers themselves, the factorial? They're always the same, right? So in the denominator, I should have the same thing as the exponent factorial. And then do you guys know how you write that it's alternating between plus and minus? Any ideas? No? So what you can do is you can do -1 raised to the n. So notice, so if n is equal to 0, what would -1, the exponent, it would be 0, right? So -1 to the 0 is 1 x to the 1 over 1, which is that first term, right? When n is equal to 1, it would be -x to the third over 3 factorial, which is the second term, right? When n is equal to 2, it would be positive again, x to the fifth over 5 factorial, which is this one. When n is equal to 3, this would be -2 times 3 plus 1 is 7 over 7 factorial, which is that one. So that's the general form for sine. We'll do more of those later. But, okay, so now for more fun. So let's see a picture. So this is what the fifth degree looks like, right? So if I want, I can keep doing this for any degree. But let's open up MATLAB and see what we can do with as far as pictures go. So this would work the same in FreeMat. Actually, I think I did this in FreeMat. But how many of you guys use MATLAB? How many of you use FreeMat? So it's the same. All right, so it's this one. Okay, so here I've put in. Let's do this real quick. What time is class over again? I always forget. Can you guys help me? What is it? 10:10. Okay. Thank you. Okay, so let's see. All right, so let's go back up just to make sure. Okay, so CLF, what does that do? Clear figure. Okay, so what we're going to do is we're going to plot. So we're going to plot sine, the sine function, and then we're going to plot the Taylor polynomials. So clear all, what does that do? Resets everything. Okay, good. All right, so right here, x is equal to, that's a -4 pi to 4 pi. And then what does the 0.01 do in the middle? What does that represent? Remember? It's like the one that you guys did. Remember you did x equals to a colon h colon b. What does h do? The number in the middle. It's the step size. So here, anytime you're going to make a plot, since when you plot, all it does is it connects dots. So if you wanted to plot a nice smooth graph, then you don't want your step size to be too big. Let me show you real quick before you. Okay, so let's say, for example, if I didn't put the number in between right there like that, what is that? What's the step size that it uses? Yeah, 1. So notice if I plot this, it'll plot it, but see how it's all jaggedy? That doesn't look like sine, right? That's because it's so each point is 1 away, so it makes it all jaggedy. So that's why I go, okay, so I want the step size to be 0.01 so that it gives me a nice smooth curve. See? Like that. Does that make sense? Okay. So, but 0.01, I just kind of picked it. If I did 0.1, that would probably still work. See? You can't even tell the difference. So either way. As long as so anytime it's jaggedy, you can just make the step size smaller in it. That makes it better. Okay, now what does this y equals sine of x do? Plugs in all of the x values into the sine function and gives back a y value, right? So now I have a bunch of x values and a bunch of y values. And so then down here, this plots the x value and then the y value. That's it. Okay? Just so you give an x value, y value, it plots a dot. And then another dot, another dot. How many dots does this have? A lot of dots, right? Do you agree that it's a lot of dots? So like if I put in right there here x, that's how many dots? 252 dots, right? Because it's 252 columns. Okay. All right. So right here, what I put in, so these I put it in manually. Or actually, I had Wolfram do these for me. And then I copied and pasted. But this is the first degree Taylor polynomial for sine. This is the second degree, right? Notice it's exactly the same as the first one. Why? Yeah, there's no, right? Because it's 0 x squared. And then I have the third degree. Does that look familiar? X minus 1/6 x cubed, right? And then the fifth degree is x minus 1/6 x cubed plus 1 over 120 x to the fifth. That's exactly what we got, right? Do you guys agree? Yes? You guys with me or without me? Right there.
What's the symbol they have in front of us? Like the
Oh, I'll go back. Let's see.
very front, like a T.
Oh, the percentage?
Yeah, why do you have that?
Oh, that's to, so if you put the percent symbol, then it won't do what's on the line. So it's like, it's the comment. So right now, I only want to have it do, I don't want it to do the 4th, 5th, and 7th, and 19th degree Taylor polynomial. I just want to do the first and the third. But actually, it doesn't really matter. I could make it do all of them. So here, we didn't do these by hand, but this is the 5th, and then this is the 7th, and this is the 19th. So the 19th looks like this very long thing that has all those big numbers. And don't worry, I did not do that one by hand. Wolfram Alpha helped me get all those numbers, because doing it by hand would be significant pain. Okay, so let's take a look. Let's plot. So this is going to plot the first degree Taylor polynomial. So T1, which is just equal to the line y equals to x. So you would expect to see something happen. What happened? Hello? Oh. Why did it do that? Okay. Anyways, I don't know why. All right, so there's my plot, and that's the line y equals to x, right? Yes? Okay. So now let's take a look at, let me get rid of that one, and let's plot the third degree. So this one should have how many humps? 2 humps, right? Probably. Oh, bless you. And so what do you notice about it compared to, so as far as approximating the function near 0, this one approximates it for a larger interval, right? So see how it follows it along for quite a bit, but then eventually it becomes not a good approximation, right? So then you go, okay, well, what if I increase the degree, right? So if I increase the degree to, what do I expect to see for the 4th degree? Exactly the same, right? So, because it's identical, because you have that 0 term, right? But when I do the 5th degree, I can have how many humps? 4 humps, right? So I would expect it to follow it along for a little bit longer. So let's see what that looks like. So a little bit better, right? See how, so the 3rd degree loses it right around there, but now the 5th degree follows it along for a little bit longer. And then what would you expect for the 7th degree? A little longer, right? So see, follow it along for quite a bit. Now, if you go really high and you do the 19th degree Taylor polynomial, you would get that it follows it for quite a while. So if you did, let's say, the 1000th degree Taylor polynomial, what would you expect to happen? Yeah, I followed along for a long time. But eventually it would not approximate it anymore, right? So a lot of great things come from this. A lot of great things. We'll talk about some of them.